given a vector field f x y, when we are talking of two dimension, and then when you are given f as x, y, z, when we are operating in the three-dimensional space, we also learned in the previous video that we have a del or nabla. If it is two-dimension, del is defined as partial x, partial y for two-dimension, and then for three-dimension, del is defined as partial x, partial y, partial z, when we're talking of three-dimension. And so, when we talk of divergence of a vector field, which is divergence of a vector div of vector field, is always defined as the dot product of the del and the vector field. Dot product of the del and vector field. And so if you are talking of 2 by 2, when we have two dimension, then we'll have our del, our divergence is given as partial x, partial y, then dot f, And so for two dimension, divergence f is given as partial f, partial x, plus partial f, partial y. And then when we have three dimension, our divergence f is defined as partial x, partial y, partial z dot f. And that also gives us partial f, partial x, plus partial f, partial y, plus partial f, partial z. And so we can see from the definition of divergence that the divergence of any vector field is a scalar quantity. It's a scalar quantity. For 2 by 2, it gives us this, it's a scalar quantity. And then for 3 by 3, it's giving us a scalar, it's a quantity. So we shall take an example. We're going to take two examples. We have where we operate on the plane with 2 by 2, and then we take one that when we are operating in space with 3 by 3. Example 1. So giving f to be equal to 4x squared y cubed minus in the I direction minus 6x y squared in the j direction. Then find divergence f. Find divergence f. So in this case, the solution will be divergence of f is given by del dot f. And we know our del is a 2 by 2 this is a problem. So del will give us partial x, partial y dot f. F will give us 4x squared y cubed in the I direction, and then negative 6xy squared in the j direction. And so if you do the dot product, where we already know the dot product, you multiply the I components, then add it to the multiplication of the j components. So we're going to have partial x of 4x squared y cubed plus partial y of negative 6xy squared. And so now I'm going to differentiate this function 4x squared y cubed respect to x. So like we learned earlier on, 4 and y cubed are constant. So we bring the constant out, 4y cubed out. If you differentiate x squared respect to x, you're going to have 2x. Now, positive times negative will give us negative. And so if you are differentiating this function aspect with respect to y, it means 6 and x are constant. So you can bring the constant out. And if you differentiate y squared with respect to y, you're going to have 2y. And so if you tidy up, you're going to have 4 times 2, which is 8xy cubed, then minus 6 to 12xy. And so for this kind of vector field, the divergence f is defined as 8xy cubed minus 12xy. And so that is the example of finding divergence of a vector field when we are operating on the plane. Shortly, we are going to look at the second example where the vector field is in space, and we are going to find the divergence in space. F to be equal to 3xy cubed I in the I direction minus 5z squared in the j direction, and then plus 4x squared z cubed in the k direction. Find divergence f. So that is we have 3 dimensions, and then we are going to find divergence of f. So the solution is going to be like this. Divergence f, we know, is the del dot f. And so the del for three dimension, there is partial x, partial y, partial z, dot the vector field 3xy cubed in the I direction, negative 5z squared in the j direction, and then 4x squared z cubed in the k direction. And so if you are finding the dot product, it means that you're going to have this dot this. You have partial x of 3xy cubed, then plus partial y of the second term, the j term, which is negative 5z squared, plus partial z of the component in the k direction, which is 4x squared z cubed. So if you differentiate all of them, now we are differentiating this term with respect to x, and so 3 and y cubed are constant. So we bring the constant out, we have 3y cubed. Now if you differentiate x with respect to x, you get 1. So 1 times 3y cubed becomes 3y cubed. Now positive and negative give us negative. Now we are differentiating this term with respect to y, and you can see that there's no y component there. So 5z squared is a constant, and we know that if you differentiate a constant, you get 0. So this one will give us 0. And then we are going to differentiate this function with respect to z. Now it means that 4x squared is a constant. So you can bring the constant out, 4x squared, and then you differentiate z cubed with respect to z. That will give us 3z squared. And so to tidy up, we have 3y cubed, then this is 0, then we have 4 times 3, which is 12x squared z squared. And so for a 3 by 3 or a vector field in space, this is how we calculate the divergence. And now to conclude this the presentation, we can see that divergence is a scalar quantity. And so, given any cross-sectional area where the force actually operates, we can have three scenarios. We can have three scenarios. So, first scenario to three scenarios. That is, the first one is we can have a situation where the divergence has a positive value. That is, divergence of the field at that cross-sectional point is 0. And what does it mean? Well, what it means is that the effect of the outflow of the electric field or the magnetic field is the outflow is more than the inflow when divergence is greater than 0. And the second scenario, when the divergence is less than zero, it means the inflow is more than the outflow. And then lastly, if the divergence of a vector field is equal to 0, what does it mean? It means that for any cross-sectional area, the inflow of the magnetic field or the electric field, taking example 3, we want to see the effects of the divergence at a given cross-sectional point. So if we have a point, let's say you have a point on the vector field, that point is, let's say, 0, 0, 1, 0, 0, 1, 0. Then it means at this cross-sectional point, the divergence F at the point P will be given as, you put 0, so 3 times 1 cube plus 12 times 0, x is 0, 0 squared times 0 squared, right? So in the end, we're going to have 3. So it means that at the point P, which is given as 0, 1, and 0, the divergence at that cross-sectional point is 3. This means that if the divergence is greater than 0, in this case, like it falls under scenario 1, it means that the outflow vector is more than the inflow vector. And so that is how we demonstrate the values of divergence. So divergence can be positive, can be negative, and it can be 0. So we'll see you in the next video where we'll look at curl of vector fields. You are welcome back, and we are still on vector calculus. This time we are looking at curl of vector fields. And curl of vector fields measures the effect of circulation of a vector field at a given cross-sectional area of the flow of the vector. So we shall move to the board, and then I introduce to you how to calculate the curl of a vector. So given a vector field F, which is x, y, z, and which has components p, x, y, z in the I direction, plus q, x, y, z in the j direction, and then plus r, x, y, z in the k direction. The curl of this vector field is defined as curl F, and it is defined as a cross product of del and the vector field, And so when we talk of curl of vector fields, it only happens in space, in 3 dimensions. And so when we have a definition of curl as as happening in space, then it means that the curl is a cross-sectional, is a cross vector. So we are going to cross del and F. And so it only happens when F is in space, 3 dimension. And so we learned in the previous videos how to calculate the cross product of 2 vectors. And it is, we use for convenience, we use the determinant of a 3 by 3 vector. So we have it's one as I, J, and K, and then del is partial x in the I direction, partial y in the J direction, and partial z in the K direction. And F is in the x direction. You have P in the y direction, Q, and then in the z direction is R. And so we learned how to calculate the determinant of a 3 by 3 symmetries, and we are using a sign table. So the first one is I. We cross the vertical and horizontal. So we'll be left with determinant of partial y, q, and then partial z, r in the I direction. Then the next one is j. J has a sign of a negative. And so j, we cross the vertical, we cross the horizontal. So we'll be left with determinant partial x, partial z, then p and r. The last, that is for in the j direction. Then the last one is the k direction, where we cross the vertical and horizontal. So we'll be left with the determinant partial x, partial y, then p and q in the k direction. And so if you open up the determinant of a 2 by 2 symmetries, we're going to have partial y, partial y, we have partial, so we have partial r, partial x, right? And then the first one, partial y, and then partial, we cross this one, so partial z. And so we're going to have partial r, partial y, minus partial q, partial z in the I direction, right? And for the j component, you have minus. We have partial x, partial z. So we have partial r, partial x, minus partial p, partial z in the j direction. The last one, we're going to have this times this. You have partial q, partial x, minus partial p, partial y in the k direction. And so when you do the cross product of 2 vectors, you still have a vector. And this is how we define the curl. F. So as usual, since it's a vector, and we want to find the curl at any cross-sectional point in the flow of the vectors, we can have 3 scenarios, like we saw in the earlier video on divergence. We also have 3 scenarios when we are dealing with curl or vector. So quickly, this one can go off, and then we'll look at the 3 scenarios. 3 scenarios, right? The first one is when we have the curl f is greater than 0. It's possible the curl f is greater than 0. When curl f is greater than 0, it means that the rotation, the effect of the rotation at that point, at a given point or on the vector, happens in the positive direction. And so that follows the right-hand rule. And so it moves, the effect goes perpendicular and it is orthogonal to the vector f. Now, that's the right-hand rule, right? hand rule, which we saw it earlier when we're introducing the cross products of two vectors. Now, if the curl f is less than 0, that means the effect of the rotation or the movement of the vector f is perpendicular but is downwards, and that one goes down, and that is the left hand rule. And then the third situation is when we have at a cross-sectional point the curl of the vector f is equal to 0. When the curl is 0, what does it mean? It means that if curl is 0, it means that this one equals to the 0th vector. And so it means that partial r partial y minus partial q partial z I minus partial r partial x minus partial p partial z in the j direction plus partial q partial x minus partial p partial y in the k direction is equal to the 0 vector. It's equal to the 0 vector. It means that if it's equal to the 0 vector, then what does it mean? It means that the first term, the I direction is 0, which means that partial r partial y minus partial q partial z equal to 0. And so if you bring this one to this side, it implies that partial r partial y is equal to partial q partial z. We can name it as equation 1. And then the j component is the same. We're going to have minus partial r partial x minus partial p partial z is also equal to 0. The 0 component in the j direction. And so it implies that if you open the bracket, this negative is positive. So negative cross the sign becomes positive. So it means that partial p partial z should be equal to partial r partial x, and that is equation 2. And then the last one is the k column, where the k column is equal to 0, which means that you have partial q partial x minus partial p partial y equal to 0, which implies that partial q partial x equal to partial p partial y, and this is 3. And so when the curl f is equal to 0, then this is a condition for conservative vector field. Then we can conclude that vector f in this case is a conservative vector field, which we saw it in our earlier videos. So on this note, we will take an example. Curl f, which is nabla or del cross f, is given as I, j, k, and then we'll have del to be partial x, partial y, partial z, and then the f in the I component is 6x squared y cubed. In the j component is 5z squared y, and then the z component is minus 3y squared. And so we're going to use the 3 by 3 determinant. So that one is going to be like this. We cross here, so be left with partial y, partial z. We have 5z squared y minus 3y squared, all in the I direction. Minus, now we come to the j direction. When you cross here, So we have partial x, partial z, then 6x squared y cubed, and then minus 3y squared, and it's the j direction. Plus the last one, where we use the k direction, we cross here, have partial x, partial y, and then 6x squared y cubed, 5z squared y, all in the k direction. And so now we need to do the 2 by 2 determinant. So we're going to have partial negative 3y squared partial y minus partial z of 5z squared y in the I direction, right? Minus, if you come here, we have partial x of negative 3y squared minus partial z of 6x squared y cubed in the j direction, and then plus this one gives us partial x of 5z squared y minus partial y of 6x squared y cubed, all in the k direction. And so we are going to differentiate. If you differentiate minus 3y squared, you're going to have minus 6y. Now, minus. If you differentiate 5z squared y, minus 5 and y are constants. And so you differentiate z squared with respect to z, you get times 2z in the I direction, minus. Now, if you differentiate minus 3y squared with respect to x, meanwhile, there's no x component. So minus 3y squared is a constant. If you share a constant, you get 0. Minus, if you differentiate 6x squared y cubed with respect to z, there's no z component here. So all these are constant. If you differentiate a constant, you get 0. So minus 0 in the j direction. Plus, now if you come here, differentiating 5z squared y with respect to x, there's no x component here. So all this term is a constant. And so if you differentiate a constant, you get 0. Minus, if you differentiate 6x squared y cubed, you see that 6x is a constant, 6x squared is a constant, bring it out. And then if you differentiate y cubed with respect to y, you're going to get 3y squared, all in the k direction. So if you tidy up, we're going to have minus 6y minus 10yz in the I direction. And you see that the j direction is 0, so it is not there. It just eliminates itself. And then we have negative 18x squared y squared in the k direction. And so this is how we calculate the curl of a given vector field in 3 dimensions. Curl only happens in 3 dimensions. And so that brings us to the end of this lecture. And I hope to see you